Good morning everyone, myself Naveen Kumar and I am back with NAN to Tetris project 2. So let's quickly go into it. Yeah, the main goal of this project 2 is to build these 5 gates: off adder, full adder, add 16, increment 16 and ALU. So we have done in the project 1, we have done the basic gates, and using those chips we have done in the project 2, we need to implement these 5 chips. Okay, so now let's quickly go into the gates. Yeah, the first one is the off adder. Off adder is a combination circuit that is used to add two binary numbers of 1 bit each. You can see this is the block diagram of off adder, and see you can see this is the circuit diagram of the off adder. Input A, input B, one sum and one carry. It's like a carry of that sum. Okay, we can see the theory part here. It does not hold the ability to consider the carry in generated from previous summations. Okay, the added with the AND provides sum and carry if present. You can say if these both are added, if sum is okay, sum will be there. If and if carry is there, in this case carry is there, so if present, the carry will be generated. And let's quickly see the off adder HDL code. See, this is the HDL code of the off adder. So now let's load the script. This is the software we already used in this project 1, so I'm not going to explain every step here already, because you already implemented there. So let's select the project 2. I'm going to load off adder here. Load the script of it, off adder. Yep, I'm going to run it. Yeah, as you can see, like if we want to know if it is implemented successfully or we are getting any errors, I already told you this. Just maximize this. Yeah, comparison successfully. Okay, it's getting correct. Let's check the output. Yeah, you see two inputs, sum and carry, and compare. Yeah, both are same, so our off adder is implemented successfully. So let's go to the next gate. It's full adder. Okay, a full adder is a circuit which has two AND gates. You see, two AND gates, two XOR gates and one OR gate. Okay, the full adder adds 3 binary digits. Okay, the previous off adder adds 2 binary digits one by one, 3 binary digits. Among these 3, one is the carry that we obtained from the previous edition as Cin, and the 2 are inputs A and B. Okay, previously we got this carry in, so okay, those are the carry in, and these are remaining 2 inputs are normal A and B inputs, and the outputs are one is sum and one is carry. Okay, it designates the input carry as the C out and the normal output as this. Okay, one is the sum and the carry, it is called as the C out. Okay, let's see the HDL code for full adder. Yeah, yep, this is the code, HDL code for full adder. And now I'm going to implement in this tool full adder, load the chip, and then script, full adder, load the script. Okay, we'll keep it to fast so that we will get implemented fast. Okay, it's done. Okay, comparison successfully. So let's check with the output. You see the same output, 3 inputs, one is sum and one is carry. This is the carry in, this is carry out. Let's check with the compare. You see both are same. Demultiplexer is done successfully. Sorry, full adder is done successfully. And let's go to the add 16. It's a logic gate which adds 2 words and a carry in, producing a sum output and a carry output, or in case sometimes overflow will be generated. Okay, you see this is the to add 2 words, and this is the carry in, and this is the carry out, and this is the sum output. Okay, add 16 adds A15 to A0, B15 to B0 and C in, and producing the sum output S15 to S0 and sometimes C out, and okay, sometimes overflow can also be generated. So let's check add 16 HDL code. Okay, this is the add 16 HDL code. Now let's implement that in this software. Okay, add 16. I'm going to load the chip now. And it's done, and I'm going to load the script, add 16. All you have to do is run. Okay, it's getting compared successfully, ended. Okay, let's check the output. You see 1A, 1B and 1 output. So now let's check the output file. Okay, let's check the compare file. Okay, see 16 bit compared file same, so it's implemented successfully. Let's go to the next one. Yeah, next one, ALU. As I said you before, it's an important one. An arithmetic logical unit is a digital circuit used to perform arithmetic and logic operations. Okay, it's perform both operations. Cool. Okay, it represents the fundamental building block of the CPU, also called a central processing unit of a computer. Modern CPUs contain very powerful and complex ALUs. As you can see, this is the circuit diagram for it. Two inputs are there, and one carry in is there, and one carry out is there. You see, in addition to ALUs, modern CPUs contain a control unit. Okay, that we know that, and most of the operations of the CPU are performed by one or more ALUs. Okay, this is a new point. As we might consider like only one ALU can be performed. No, there are multi tasks going on, like multi ALUs will be there in the CPU. Okay, now let's check the ALU HDL code. Yeah, this is the HDL code for ALU, and now I'm going to execute in this software. First I will be selecting the chip, ALU chip, and then I'm going to select ALU, not ALU non-stat, which will be doing it later. And now I'm going to show you how it will be. Okay, it's getting executed, comparison rate successfully. Let's check the output. You see, this is the output. As we cannot verify, so I am going to verify it manually using this compare. Okay, so you see both are same. And now I will be loading this ALU non-stat script so that I will show you the difference between these two. I'm going to run this. You see, it's getting executed, and now I will show you the output. This is the output, which is different from the previous one, and I'm going to compare it. You see, all are same. So let's go to increment 16 file, HDL code I'm going to show now. Increment 16. You see, this is the HDL code for increment 16. And now I will be loading that into the software. Increment 16, load chip, and I'm going to increment 16 load script. All I need to do is run. Okay, it's getting executed correctly. Check the output. You see, one is input and this is the output. Okay, you can see that incrementing last bits, and I will check with the output. You see, both are same. So now project 2 is over. We have implemented the 5 gates using the chips which I already have in the project 1. So 9-to-Tetris project 2 is over, and this is the end of the 9-to-Tetris project 2, project 1, and both are completed. So thank you.